Right now I am going to design this flying wing again for you to learn how to do, and after that I'm going to simulate it in AnsysFluent to find the proper point for placing the center of mass. Okay, I open a new part and just do it again. In front plane I make a sketch, coming back here and just copying this profile here. I just paste it. Okay. Here on this sketch, exit this sketch first. Just highlight it and Ctrl plus C. Coming here, Ctrl plus V, centering, yeah, and I just want to place this to the coordinate system center. Just let's move it out these values 423 and 108, or here sketch, move entities from 2. I put it here to here. Okay. Now if you click on this point, the coordinate is 0 for both x and y, and just finishing this isometric view and creating a plane parallel to the front plane with a 20 centimeter far from it. Yeah, this much, yeah. And now sketching profile on it. I copy this profile and come here, Ctrl V. Right now moving it first from here to here, and right now I'm going to translate it about 30 centimeters backward. For example, this much. Done. Here again, isometric view. I have no mouse right now, and I'm just doing all the things with laptop pad, touchpad. It is somehow a little difficult. I select these two sketches and come to feature, loft boss. For example, here again I'm going to create a plane from plane 1 with 60, 80. This is an absolute value, I think. Okay, and now click on it, sketch on it, come here and from the second loft select this sketch and copy, Ctrl C, come here, Ctrl V, move it first to from here to the central coordinate system, apply it again, isometric view from oh, I forgot to translate that. Let's see how much. It seems it is not very much. These two profiles just a little backward. So I come here and again edit this sketch, and I move it for about, for example, this much. Apply. Now I create a second loft, this profile with this one, into features, lofting. Just put this forward, apply it. Okay, let's look from top. Oh, it is not like that. Let's change the amount of. First, let's make it visible so we can see the amount of translation properly. Do it moving here. Let's go backward. For example, this much, about 300. Okay. Now let's view it from the top. Yeah. It is somehow like this. Here, so I should do a little more. This one comes forward, this one goes a little backward. So here I edit it, move it. For example, 5. Move it, for example, for 5 centimeters. Let's again look from top view. Okay, and let's make this one a little translation to backward. Move it for about 5. Okay, confirmation. Yeah, it's not bad. Okay, right now I'm going to extrude this part. Yeah, here. This is sketch. Extrusion for 7 centimeters. Change direction, reverse it, confirm. Again from top view, just let mirror all these things. The program asks for a mirroring plane, so I choose this, delete this, and bodies to mirror. I choose all the entities, there is just one body till now. Okay, from the top view, this is the flying wing. Okay, I'm going to export this geometry for simulation and doing some CFD in AnsysFluent to find the proper point for center of mass. Right now, if you think if we construct this flying wing with a homogeneous material, for example, all the parts are from styrofoam, and there are no other elements like motors, propellers, battery, or other things. It's just a solid styrofoam part. For example, in evaluate tab you can find the mass center. As you can see, the mass center is about 34 centimeters back from the nose, this here. But as you will see, we are going to simulate the airflow around this flying wing at 0 and 5 angle of incidence, angle of attack, and see that what point as the center of mass will give us the proper stability. As you know, a stability of a flying wing is somehow challenging. Okay, I just save it here with a name, for example, flying wing. Okay, save it, and after that I export it for sat.sat file with the name flying wing, and I come here, I open a workbench, Ansys workbench, to do the rest. Well, let's go on. From the analysis systems, choose the Fluent. There will be a block here with all the modules in it: geometry, mesh, setup, and processing the results. Right click on geometry and choose design, new design modeler geometry, or here we have a already one, import geometry. Browse it, go to the place you put the SAT file here, open it, and after that again right click and choose edit geometry in design modeler and wait for the design modeler to come up. Well, here is your import generated, and wait for the part to appear. After that we are going to create a domain. Here we have the part. Let's create a box around it from create primitives, box with dimensions. As you can see here, top view, this is the center of coordinate systems. Okay, we need here this extrusion was 7 centimeters in half, so 14 centimeters in total. So let's create the box in X direction, for example 50 meters, in Y for example 20 meters, and in Z again 20 meters. Okay, as you can see from the top again, it's going to the left, so we need to place the plane in the middle. So translate the box for in X direction minus 10 meters, in Y dimension again minus 10 meters, and in Z directions there is no need for translation. Generate the box from the top view with the view. As you can see, this is the plane here. Let's rotate the screen. We need to translate the plane in positive direction of Z for 7 centimeters. I want this plane of box to cut through the plane exactly in half. Okay, so I choose this part, which is the plane, and create body transformation, translate, and here bodies, this is the plane, apply, direction, selection, coordinates, just for Z 7 centimeters, which is 0.07. As you can see, there is a preview which shows the right value of translation. Okay, just generate it. So the plane moved the proper value. Well, right now I'm going to subtract the plane from this box. So come here and choose Boolean, and from here change the unite to subtract. Target bodies, the box is target, the plane is tool body, apply, and just generate. As you can see, they have all the plane is disappeared and is subtracted from the box, as you can see. Okay, with the view. Right now here in design modeler we do not have anything more to do. Just save the project if you want. For example, I go here on desktop and with a name, for example, flying wing. Okay, save it. Then you should go to mesh module. Just right click and edit and wait for it to start. Well, right now just come to mesh tab. As you can see, there are some default settings. First, do not change anything and just generate the mesh. Let's see what is going to be done by the default settings. Okay, well, let's rotate it here, let's zoom here. As you can see, the mesh is very coarse. we are going to refine it. Come to mesh here and do some sizing. For example, for curvature minimum size, here make it 1 centimeter. There is an error which says this one should not be greater than that one, so make it again 1 centimeter. Okay, generate the mesh again, and let's see what is going to be done. I'm going to put boundary layer mesh either. Well, as you can see, it is better than the last one. Here the mesh is increased. If you want to know the number of cells, just come to statistics and see it here. Watch it here. 115 and 100,000 and 150,000 almost, approximately. Okay, I want to add an inflation or boundary layer mesh. Select inflation, choose the main geometry, fit the view, align it through Z, for example. Just here, select it. No, just the mode, selection mode to box select again. As you can see, the plane is selected, applied, 9 faces. Okay, and as for the method inflation option, put it to total thickness, and for example for 3 millimeters and 10 layers of boundary layer. Just generate it and wait for the program to generate the mesh. Well, come to mesh, let's rotate the view and see the details here. Well, as you can see, there are 10 layers of boundary layer mesh, and as you can see again, the mesh is somehow refined. Okay, and the number of cells is about 200,000. Okay, well, right now I'm going to name some boundaries and domain. Just click, right click here and select name selections. Okay, the first one, choose the type of volume and mode type to single. Select all the domain. This body, as you can see, it is a volume type. And for the second one, select the surface. This is the symmetry. Okay, let's name them. Highlight it and press F2. Write scene, for example, for symmetry, or any other name you like. And the first one, for example, I type it Floyd Air or anything you like. It's just a name. The third one, I choose all these. Okay. This. Press the Control key and select all of them together. Okay. All these 4 faces as the velocity, let's rotate it for the outlet. F2, this is for example velocity, for example name, just a name. Right now this is for example outlet, and the last one is the plane. Just align by Z direction, change the mode type to box, and just drag this region, apply 9 faces which are your plane, and the name, for example flying wing. Okay, everything is okay. Just save the project, not to lose the settings you've made. Okay, let's go to workbench. Again, right click on mesh and just update it. After that, right click on setup and wait for AnsysFluent to be started. Okay, let's just display all the domain we have done. Line, wing, edges displayed. Just fit the view here, as you can see. This is the plane, half of the plane. We are going to simulate half of the plane because of less grid cells and less time for simulation. Okay, but let's just do the settings. First, check the mesh, everything is okay. There is no need for scale. As you can see, the domain range is just as it must be. So let's do it. The first general settings are the ones as we like. Models, energy is off, viscosity, SSDK omega. Okay, we are not going to insist right now on turbulence, because the main forces to consider for CG position are the pressure forces. So drag and viscous forces are not very important right at this point. Okay, outlet, symmetry, all day, and these all these boundaries are have been given the right time, except for velocity. Do it velocity to velocity inlet, and just let's do it magnitude and direction. For example, if the plane is going to have 20 meters per second of velocity, for example, and this is the direction as it is. Okay, the valve is flying wing, and just let's create a force report. The force report, for example, the lift force, just change the direction to perpendicular, and report file, report plot, for example, for flying wing. Okay, well, just come to initialization and hybrid initialization, and let's after that go to run calculation. And before starting the calculation, for example for 20 number of iterations, before anything you go on, just save the project. Yeah, and just click the calculate button and let the program start estimation. Well, let's see. As you can see, force is not stable right now, so some more iterations must be done. For example, 50 more. And before starting the calculation, just go to monitors tab and residuals and make the condition of convergence somehow tight in order to make the program go on and not stop by that condition at first. Okay, again, let's make the calculation continue. Yeah, it must go until this graph goes horizontal, or lift force gets stable and constant. After that, we can go and post-process some of the results. In fact, this simulation, I'm not going to insist on scientific and academic accuracy here. Just a rough estimation for you to know where your plane, where your aircraft, RC plane, UAV, CG, center of gravity or center of mass is light, or so you know how to arrange all the components, batteries, autopilot or avionics stuff, engines and all other things. You must arrange them in a manner so that the center of mass is at the point where this program suggests. Okay. Well, I did some more 50 iterations. As you can see, the graph is somehow stable and the force has been constant. Let's just have a rough look at the contours of pressure. For example, here, flying wing pressure, display. Shut down, unfortunately. Okay, just take a look at pressure contours. As you can see here, the pressure is goes high at leading edge and goes below on top surface. Relatively higher pressure on the downside of the wing. Okay, just let's have a look at the amount of force and moments. Here come to reports, forces, and just change the direction parallel. Lift force, flying wing, cranes. Well, as you can see, the total lift is about 7 newtons, which means 700 grams of lift force. If you want to state it in mass content, meaning as for this is the half, it's a half of the plane, so you should double it, so about 1.5 kilograms. So at zero angle of attack, with a velocity of 20 meters per second, the plane generates about 15 Newton or 1.5 kilograms. Just let me take a look at moments. Pitching moment we need here. So moment center, for example, moment center is if you put the moment center for example at the middle of the fuselage, just look it here. Again, I want to show you this point is in coordinate system. Here this is about 56 centimeters, so 25 or 27 centimeters is in the middle. Okay, come here and put it 27 centimeters, and these two Y and Z are 0. Pitching moment is in Z direction, so this is 1. Just let's print it. Well, as you can see, the total value of moment is positive. If I take the moment center more backwards, for example 29 centimeters, it is again positive. Let's do it, for example 35 centimeters, it is negative. So let's find the point where it is near 0. For example 33. Print it here. Okay, about 33 centimeters or 32. Yeah, about 32 or 33 centimeters from the most forward part of the plane. It is the point where moment is 0. So you should place your center of mass somewhere a little more backward from the 30. For example, somewhere here, a little more backwards. You should place your center of gravity. You should arrange the components so that your center of gravity comes to, for example, 35 centimeters to have a stable flying wing. So let's again simulate this flying wing for an angle of attack of 5 degrees. Come to boundary conditions, and in inlet, velocity inlet, just let's change the direction of the flow. Here it is 100. Just let's calculate cosine and sine. By 5 degrees, this is degrees, so this is cosine. Let's just copy. Come here, just paste it. It was not copied. 9962. Okay, 9962. And as for the sine value, again by trigonometry, sine value is 0872. 0872. Apply it and just calculate the simulation for this angle of attack. Well, as you can see, the lift force goes up. Well, we wait until this gets on and finished. Well, it is done. As you can see, the lift force has increased, and about the value come to force reports. Yeah, print it. As you can see, it is about 8 kilograms. It's about 40 newtons. Double it for the whole geometry, which is about 80 newtons, which means about 8 kilograms of force. So the weight of the plane could be about 8 kilograms. It means if your plane is heavier, you must increase angle of attack. For 5 degrees of angle of attack, the lift force is about 8 kilograms. And as for the moments, as for the pitching moment, at this point, 32 centimeters behind the flying wing ahead point. Well, as you can see, it is a positive value. Just let's increase here. It is minus value, so 34 centimeters. Minus again, 33 centimeters. It's positive, as you can see. So at 0 or at 5 degrees of angle of attack, as you have seen, the point where pitching moment is neutral or near 0 does not change. For both cases, the center of mass or the neutral point is about 33 centimeters behind the tip, behind the head of the plane. So you should arrange your components inside fuselage somehow that your center of mass gets to 35 centimeters, about 2 centimeters behind the proposed neutral point, somewhere here, for example. To make your flying wing stable during flight, it is very important. If you have any other questions about this simulation and estimation, just let me know. I would be happy to help. I put some of these files, for example the mesh file, the .sat file or solid part file, in the description below, so you can do the simulation for yourself. Be safe and happy, and goodbye.